Hello. In this video, we will look at another common case of motion in 2 or 3 dimensions, projectile motion. Projectiles include such things as basketballs, bullets, the stones flung by trebuchets, and even intercontinental ballistic missiles during their unpowered phase. Now, in physics, in order to solve complex problems, we often make assumptions that simplify the problem. It's perfectly valid to do so. However, it is important to state your assumptions when you make them. If you do so, you will know when your new solution to the simplified problem is valid and when it is not valid. So what about projectile motion? When treating projectile motion, we will assume that the projectile can be treated as a point particle. So in other words, we won't care about the extension of the object. If we throw a tennis racket, we're still going to treat it like a point particle. We're going to ignore forces such as air resistance and lift. We will assume that the only force acting on the projectile, and thus the only cause of acceleration, is gravity. This is the most crucial point in the definition of a projectile. Because of this, we can't treat curveballs or skydivers or rockets when they're in the powered phase. Curveballs because their interaction with the air causes them to curve their path, so it's not just the force of gravity. Skydivers because not only does gravity act on them, but also air resistance. And rockets when they are being powered, because again, it's not just gravity, it is the thrust of the rocket that also acts on them. In spite of all these cases that we can't treat, there are still a lot of things that we can. So, let us look at projectile motion. There's only one force acting on the projected object, on the projectile, so let us orient our axes so that the force of gravity is acting only in one direction along the y-axis. Okay, and traditionally we take it to be acting in the negative y direction. However, if the force of gravity, which is the only force in this situation, is acting only along the y-axis, that means there is no force in the x direction. However, we will see later on in this course that F net is equal to ma. But this implies that the components on either side are equal. So Fx is equal to max. If there is no force in the x direction, that means there is no acceleration in the x direction. And if there is no acceleration in the x direction, this means that the x component of the velocity, vx, will be constant. After all, acceleration is the rate of change of velocity. So if the acceleration is 0, that means the velocity is not changing. But this only applies in the x direction. The great secret of 2D kinematics is that the motion in the y direction is usually independent of the motion in the x direction. So what we will do is take this original starting velocity vector and split it up into y and x components. So these are the vertical and horizontal components, and here we can see the relation to the overall velocity vector. Notice how the size of the two components determines not only the size or the magnitude of the total velocity, but also the angle. So now, what happens as our projectile moves? As we have just said, there is no acceleration in the x direction, so the x component of the velocity stays constant. So that stays unchanged. However, there is an acceleration in the y direction, and it is pointing in the negative y direction. And so the velocity in the y direction starts to change. Initially it was very large and pointing upward, and now it is somewhat smaller and pointing upward. As that happens, look at what happens to the overall velocity vector. The x component has stayed the same, but the y component is smaller, and so the overall speed is now smaller. This velocity vector is smaller than this initial velocity vector. Also note the change in angle. Earlier, the y component was much larger than the x component, and so the angle was much closer to 90 degrees. Now that the y component is decreased, the angle has changed. Let us keep on following the projectile. Here it is just before reaching the top. And upon reaching the top, what happens? At that point, the y component of the velocity is 0. If it wasn't 0, the projectile would continue to climb and would go higher and higher. But because it is 0, that is the turning point, and that is the maximum height. However, notice that the total velocity is not 0. There is still an x component, the same constant x component. Now, if we go beyond that point, the acceleration starts to cause the y component of the velocity to point downward. The x component continues as before. But now, due to the change in signs, we can see that the overall velocity is pointing to the right and down. Following it on, we see that the y component gets stronger in the negative direction, and the x component stays unchanged. Eventually, the projectile will hit the ground, and at the moment of impact, its velocity here is once again pretty large in magnitude. So, how do we describe this motion mathematically? This is a case of constant acceleration. Let's treat the x and y components separately. For the x component, we have x of t is equal to x naught plus vx naught t plus 1/2 axt squared. And it's important that you put the x subscript so that you don't confuse them with the y components. In this case, we know that ax is 0. And so this equation simplifies to x of t is equal to x naught plus v naught t. Looking at the y position, we see that we have a similar expression, except now we know that ay is negative g. So these are our two expressions, one for x as a function of time and one for y as a function of time. Supposing I want to plot this trajectory in the xy plane. In other words, I know that the trajectory looks something like that, but what kind of curve is it exactly? To do this, I need to eliminate the variables from these two equations and express y in terms of x. If I examine the expressions, I see that the only variable is t. So we need to eliminate t. I could eliminate t using this or using this, but obviously it's much easier to get an expression for t using this simple linear expression. Rearranging it for t, we get this, and then we plug this in into the y equation. So we get an expression for y as a function of x and various constants. Now, of course, this looks fairly complicated. I don't expect you to memorize this. I brought this up simply to point out one thing. Y is a quadratic function of x. Here's a linear term, and then you can see that somewhere in here is a quadratic term of x. So, y is a quadratic function of x, and it turns out projectile motion traces out a parabola. Typically, in these problems, we are given the muzzle velocity, that is, the speed v0 at which the projectile is launched, and the angle theta at which it is launched. How do we calculate Vx0 and Vy0 from V0 and theta? Drawing a simple diagram, we see that we can use trig functions to get the components of V0. Specifically, drawing a right-angled triangle, we see that Vx0 is equal to V0 cosine theta, and Vy0 is equal to V0 sine theta. If we want to go in the other direction, we notice that Vx0 squared plus Vy0 squared will give us V0 squared, and so V0 is equal to the square root of Vx0 squared plus Vy0 squared. Similarly, if we divide Vy0 over Vx0, then we get tan theta. So, using these relations, we can get another form for the trajectory equation. We get y as a function of x again, and we can see more clearly the dependence on theta. However, instead of trying to memorize those complicated equations, it is simpler to memorize the constant acceleration equations, which are much more versatile. We focus on just this, and then these simple relations that relate the overall magnitude of the initial velocity to its x and y components. From these equations, we can derive all the results that we need. Thus, these equations are much more versatile, and they can be used in a lot of cases. As an analogy, if you had an exam on Sudoku, you wouldn't memorize Sudoku, you would learn the tricks to solving Sudoku quickly. Alright, the techniques that are generally applicable to all Sudoku. In a similar way, these equations are much more versatile. Now, if in addition to all of this, we make an additional assumption that the landing height is the same as the launch height, in other words, a situation like this but not like this or this. So, if we focus on this case, where the landing is at the same height as the launching, we can make a few more statements. So, going back to the trajectory equation, we know that the position in the y direction, that is the height at t final, is equal to the launch height. So we can cancel out those two terms. We're left with this. This is just simply the same equation rewritten. But x at t final minus the initial position is simply the range, the horizontal range covered by the projectile. If we call this range r, then this equation looks a little bit neater now. We simply replace these terms, x final minus x naught, by r. And now we can rearrange and solve for r. So, assuming that the launch height and the landing height are the same, we get an expression
for the horizontal range? It's really quite simple, and notice that it depends only on three things: the muzzle speed, the launch angle, and the acceleration due to gravity, g. But remember, this is only in the special case where y final equals y naught. Here again is the expression for the horizontal range. Usually, we like to throw things further. So, how can we increase the range of a projectile? Let's look at the three factors. G is usually a constant, or at least something we can't control, but it is worth noting that in different places, because the value of G varies from place to place, the same launch speed can lead to different ranges. As seems fairly obvious, if the launch speed v0 is increased, then the range will increase. In other words, if you throw something harder, it will go further. We also note that the range depends on the angle, theta. However, it's not as simple as increasing theta always increases the range. We notice that sine 2 theta reaches a maximum when 2 theta is equal to 90 degrees, or in other words, when theta is equal to 45 degrees. That is, theta equals pi over 4 radians. This will give us the maximum range. So, theoretically, assuming no air resistance and keeping the launch speed constant, we will find the greatest range for a projectile when the launch angle is 45 degrees. Why does this make sense? Think about it a little while. We'll come back to it a little bit later in this video. Again, remember that we were assuming that air resistance is negligible. In reality, of course, depending on the speed at which you throw something, air resistance can be a powerful force. Also, if you're looking at cases like a shot put, the fact that it is easier for the human body to throw at some angles compared to others is another reason why shot putters don't throw at exactly 45 degrees. Let's look at some other properties of this projectile motion. What can we say about the greatest height reached by a projectile? In fact, what does the greatest height imply about the projectile's motion? At the greatest height, we know that since the y-coordinate has reached its maximum value, Vy must be 0 at that time. So let's figure this out. We use one of our constant acceleration equations. We know that Vy final will be 0. If we call y final minus y naught h, then we have this simple equation. Solving for h, we get Vy naught squared over 2g. And you can see that the units work out. On top we have meters squared over seconds squared. In the denominator we have meters per second squared. And in the end we just have meters. What about the time it takes to get to the highest point? Well, again, we know that the final velocity is 0. We know that ay is minus g, and we solve for it. So the time it takes to get to the highest point is Vy naught over g. This corresponds to half of the flight, assuming that the launch and land heights are the same. So if we simply double it, we will get the time for the full flight. We can call this the time of flight, and its value is 2 Vy naught over g. Again, the units work out. In the numerator we have meters per second, in the denominator we have meters per second squared, and so the final result is simply seconds. Here are those two results again. The height is Vy0 squared over 2g. The time of flight is 2 Vy0 over g. And since Vy0 is V0 sine theta, we can also write those expressions like this. Notice an important point. All that the maximum height depends on is Vy0. That is, the vertical component of the launch velocity. All that the time of flight depends on is Vy0. In both cases, of course, I'm assuming that g is constant. But assuming that g is constant, all that determines how high a projectile goes and how long it is in the air is Vy0. This is quite important, especially when you compare two different projectiles. Let's look at another way to find the time of flight. Here is an expression for y as a function of time related to the various constants. If we assume that the launch height and the landing height are the same, then we can cancel y and y0, and that leaves us with this equation. However, y is equal to y0 at the end of the flight, and so this t that we have here is the time of flight. We can solve for it, and we see that y is equal to y0 either when t is equal to 0 or when t is equal to 2 Vy0 over g. T is equal to 0, of course, corresponds to the launch point, and t equals to 2 Vy0 over g corresponds to the landing point. Finally, let's look at another way to derive the range, and this is a much more general way. We think of the range as x final minus x naught. However, we know that in the x direction there is no acceleration, and the velocity in the x direction is constant. In that case, the change in x is simply Vx0 times the time of flight. As long as the projectile is moving, as long as it's in the air, it has a constant x velocity, and that determines how far it moves in the x direction. However, we already have an expression for time of flight, and that is 2 Vy0 over g. So Vx0 times 2 Vy0 over g gives us the range. If we plug in for Vx0, we get V0 cosine theta, and for Vy0 we have V0 sine theta, and this is the expression for the range, which you can check is the same as the one we derived before. Again, we have assumed that the initial height and the final height are the same. However, even if they're not, we can still go up to this point. As long as we can figure out Vx0 and the time of flight, that will give us the range in any case. Going back to this expression, we notice that the range depends on both Vx0 and Vy0. So, unlike the height, which only depends on Vy0, the range depends on both the horizontal and the vertical component of the launch velocity. Now we see why 45 degrees gives us the greatest range. If we have an angle greater than 45 degrees, then Vy0 increases over Vx0. This helps increase the time of flight, so the projectile is in the air longer, but it doesn't cover much distance horizontally because Vx0 is smaller. If we decrease our angle below 45 degrees, then it's moving faster in the x direction, but because the y component of the velocity is not very large, it doesn't stay in the air very long, and so again it can't cover much distance in the x direction. The best compromise between these is at 45 degrees. So, keeping in mind all that we've looked at so far, try and solve this question. The two projectiles shown are A and B. They are thrown at the same time. Which one lands first? Think about it carefully. We will now discuss the answer. We know that the time of flight is proportional to Vy naught. So, in other words, the one which lands first has a smaller time of flight, and so it must have a smaller Vy naught. But we also know that the maximum height reached by a projectile is proportional to Vy naught squared. So, if we want the projectile that lands first, that is a small t, then it must have a small Vy naught. If it has a small Vy naught, then it must have a small h. Looking at A and B, it is clear that projectile A achieves a greater height than projectile B. So that means projectile B will land first. Projectile B has a lesser height. Because it has a lesser height, it must have a lesser Vy naught. Because it has a lesser Vy naught, it must have a lesser time of flight. And so the answer is B. Here is the explanation given in more detail. You can pause and read it at your leisure. We'll be moving on to the next slide. Here's another question. In this case, projectiles A and B launch and land at the same point, but not necessarily at the same time. Which projectile has the greater Vx? Take your time and think about it. We will now discuss the answer. Consider this. Vx is equal to the change in x over the change in t. The change in x is the same for both of them. So, the projectile with the greater Vx must have the smaller delta t. Right? Because a smaller delta t here in the denominator will give us a greater Vx overall. But we know that the time of flight is proportional to Vy naught, and that Vy naught squared is proportional to the height. So once again, the smaller time will correspond to the smaller Vy naught, which corresponds to the smaller height. B covers the same distance in x, but in less time, and so it must have the greater Vx. Again, you can pause and read at your leisure. We'll move on to the next problem. Here is a typical projectile motion problem. A man standing on the roof of a 15-meter tall building throws a rock with a speed of 30 meters per second and at an angle of 30 degrees above the horizontal. Let us look at the following questions. First, let us calculate Vx initial and Vy initial. Well, we know that Vx initial is equal to V naught cosine theta, and so that becomes simply 30 meters per second cosine 30 degrees, which is 26 meters per second. Similarly, we can go ahead and calculate Vy initial, and we find that Vy naught is 15 meters per second. We note these values for the future. We are asked to create a table of our knowns and unknowns. Remember to look at both the x and the y values. Here we have listed all the information that we could get from the problem. We take the building to be the starting point along the x-axis, and so x initial is equal to 0 meters.
we take ground level to have a height in the y direction of 0 meters, and so y initial at the roof of the building is 15 meters. We have previously calculated Vx initial and Vy initial. We know that Ax is 0 because there is no acceleration in the x direction, and that Ay is negative 10 meters per second squared. Finally, if we look at our stopping point as being when the rock hits the ground, then y final is 0 meters. Here we are asked to find the final velocity of the rock just before it hits the ground. Remember, velocity is a vector. The x component is simple because we know that Vx final is equal to Vx initial since Ax is 0, and so Vx final is simply 26 meters per second. But what about Vy final? To find Vy final, we simply use one of the constant acceleration equations, but specialized to the y direction. And so we have Vy final squared is equal to Vy initial squared plus 2ay times delta y. Plugging in numbers, we know that Vy initial is 15, so we have 15 squared. We know that ay is negative 10. And finally, delta y, which is y final minus y initial, is 0 minus 15, and so we have negative 15 there. Putting that all together, we find that Vy final squared is 525 meters squared per second squared. We know that there are two possible routes to this equation, but we know that when it hits the ground, the rock will be traveling downward and to the right. So the y component must be negative. So we will take the negative square root. And so we find that Vx final is 26 meters per second, as it was in the beginning, and Vy final is negative 23 meters per second. Putting it all together, we find that the final velocity of the rock just before it hits the ground is 26 meters per second I hat minus 23 meters per second j hat. Remember, velocity is a vector. We are now asked for the speed of the rock just before impact. Having found the velocity, we know that the speed is simply the magnitude of the velocity. And so we simply use the Pythagorean theorem . Notice how the minus sign disappeared upon squaring. And finally, we get a final speed of 34.7 meters per second. We are then asked to calculate the angle that the rock's final velocity makes to the ground just before impact. Once again, we start with the velocity vector. We can see that the rock is moving to the right in the positive x direction and downward in the negative y direction. So it will make some angle below the horizontal. We can use a simple right-angled triangle to figure this out. This is how the triangle looks. Since we know the values of the adjacent and the opposite, we can use the tangent function. So we have tan theta is 23 over 26, and solving for theta, we have that the angle the velocity makes is 41.5 degrees below the horizontal. Finally, we are asked to calculate the distance of the impact site from the base of the building, in other words, the horizontal range. We know that the range will be the horizontal velocity times the time of flight. We know what the horizontal velocity is, so we simply need to find the time of flight. There are two ways to find the time of flight, using 2 out of the 3 constant acceleration equations. Since we already know what the final vertical velocity is and what the initial vertical velocity is, I will use the simpler v final equals v initial plus at equation to find the time, specializing it to the y direction. I first solve for the variable that I want, which is t. Upon getting this expression, we now plug in the numbers. Simplifying, we find that the time of flight is 3.8 seconds. And so, the range would be given by 26 meters per second times 3.8 seconds. This gives us a range of 99 meters. And so the horizontal range covered, that is the distance of the impact site from the base of the building, is 99 meters. That brings us to the end of this video. I'll see you in the next.